How's it going, AS Math? It's Mr. Knight, still under the weather, still at his house, but I'm bringing this video lesson to you guys to get a little bit of trig graph review. Did I just say trig graph review? Oh God. We're going to be more than okay, guys. Here's the thing about this. I just played a funny sound. Tried to. Here's the thing about these guys. They're not going to be bad because they're pretty predictable, and that's why we're doing the review. Get you guys a bit more confident with this stuff, okay? So we're going to jump into this and kind of take a look at what we got here. And I'm trying to zoom in, not on my face anymore. There we go. That's way better. Still won't let me zoom in. I want to zoom into this, man. Okay, there we go. I figured it out. But now you just see now you just see my eyes. I'm having too much fun. Sorry. Okay, we're jumping in, I swear. So the trig graphs, they, sine, cosine, tangent, all have their own unique graphs, and they all have this periodic nature. So I'm going to make an xy or a theta y table. So my independent variable is my angle, and then my y value is what this trig function spits out, just like normal. So what we're going to do is just go through some of these nice angles. They're really nice angles because sine of 0 is just 0. So 0, 0, I'm going to plot right here. By the way, too, before I even keep going, if you already are comfortable with the base functions and you just want to skip ahead to making the stab foldable handout, which I have later in the video, which is something you can use on your tests, go ahead and just skip ahead in the video until we get to that part. You'll see it because it'll be right after we get through this sine, cosine, and tangent. Okay, so right about when we get to here in the video. I don't know when that's going to be, so we're just going to roll, okay? But yes, 0, 0 is one of my points on the sine graph. Sine of 90 is 1, so I'm going to plot that. Sine of 180, that actually comes back to 0. Sine of 270, we're at -1. And back at 360, sine of 360, which is the same as sine of 0, is 0. And again, the reason I picked these is because you can see this is really just some easy values to plug in. I didn't do a whole lot of thought with it. And in fact, whenever you are trying to graph your sine, cosine, tangent function, the base angles and the base chart that I give you, utilize that. Utilize what we know and make these problems a lot simpler for yourself. You're going to see more of why that's apparent later on. And again, this guy's periodic, so if I got a sine of -90, okay, I'm going clockwise on my unit circle. That lands me at 270 degrees, so I'm down here at -1 again, and it'll just pop right back up. All right, let's look at cosine. Cosine is very similar to sine, but it's a little bit different. So cosine of 0 is actually 1, right? So it actually starts up here. Once we get to 90 degrees, cosine goes to 0. Cosine of 180 is -1. That makes sense. When we go to 180 degrees, the x-coordinate has got to be -1. And that's what corresponds with cosine of theta on the unit circle. Cosine 270 back to 0. And cosine of 0 or 360, we are back at +1. So, and again, -90, we're back at 270, so we get back to 0. So this guy just has, once again, a periodic nature, very similar to sine in this regard. And here's the thing about both graphs. So both graphs have something we call a period of 360 degrees, meaning from 0 to 360 degrees, this pattern just duplicates over and over and over again along the line. Okay, so it's like basically copy and paste before copy and paste was even a thing. Okay, sine and cosine were doing it way before then. Right? And the same thing with sine. To complete one full cycle to get back up to 0 took 360 degrees. It's also got this wave-like pattern. Useful to note because it makes sense. We're taking it from a circle. That is where it's coming from. But also, this is really useful for applications of mechanical waves, light waves, electromagnetic waves. Any waves really have something to do with sine and cosine a lot of the time. And in fact, sine theta is the same thing as cosine theta minus 90 degrees. So all it is just offset by 90 degrees. Otherwise, they're pretty much the same exact function, interestingly enough. But let's move to tangent, because tangent's weird, man. I'm not going to lie to you. I'm not going to sugarcoat it. Tangent's weird, but it's also periodic. And looking ahead, it's got a period of 180, asymptotes. If you don't know what an asymptote is, you're going to just get reminded very quickly. So let's look at this. I've already went ahead and I kind of changed up what tangent is going to look like. I'm going in multiples of 45 degrees now, right? So if you do tan of 0 degrees, you get 0. That makes sense. But if I do like tan of 45, I get 1. Tan of negative 45, I get negative 1. Okay, so I'm going to plot those. And this is what we end up kind of getting so far. It almost looks like a straight line. It's very deceiving. When you do negative 90, if you do tangent of negative 90, you actually get an error, meaning it's undefined there. And this is what I'm talking about in terms of the asymptotes. An asymptote is basically a domain value or an x value, or in this case, a theta value, that cannot actually be used in your trig function because it means that there's no value there. So what happens is your tangent function is going to get really, really close to that asymptote line, but it's never going to cross it. And likewise over here. Meaning you can get really, really close. So if you did like tangent of 89.9999, so on and so forth, you get a really high y value. You can't do tan of 90, okay? It doesn't work. And this pattern repeats itself just like sine and cosine, only it's a period of 180 degrees from here to here, right? So it's basically a copy and paste. So predictively, tangent of this guy right here, I know it's going to be at 0, and it's going to look something like this. I think I messed that up. 180 degrees. Yeah, there should be... Oh, no, there's another asymptote at 270 degrees. I actually messed that up. My bad. This guy should be right here instead. And this guy should actually be at -1. This guy should be at +1 if we had like plus like 225 degrees. And then 270 degrees. Yeah, that's better. That guy is our asymptote right there. Should be a period of 180. So that is my mistake, guys. I am sorry about that. So just kind of get rid of that guy. We don't need that guy. Looks like that guy a little bit more. Okay, a little bit better. So this guy would be up here 1. This would be in the middle. Look something like this, and at least this side is fixed. Okay, kind of looks like crap a little bit. All right. Here's the thing. As long as you know basically what this guy looks like, you know what the other parts look like. So it's not the end of the world, okay? It's not like I totally ruined it either. It's fine, but that's pretty bad, okay? So yeah, there's asymptotes at these angles, which is also why I realized my mistake. Now, these trig functions, they have general forms, meaning they actually look more like this. This is actually a better way to represent them in general, because we don't always just get y equals sine theta. No, we might have different parameters or transformations that are going on. Now, this may seem a little overwhelming, but actually, these 4 parameters each do something very distinct, and we're going to make a handout out of it in just a little bit. So, first of all, let's actually review some of those guys. Okay, so here we go. By the way, if you want a clean version of tangent, here it is, baby. Here it is. This looks way better. Okay, cool. Let's come over here to our general form of what I got. Now, this is, right now, just sine x. Normal, good old sine. And this is what each of these are going to do, okay? We're going to go through each of these, and then what we're going to do is we're going to put it on a foldable. So we're going to make that foldable right now. So what I need you to do is get out a separate sheet of paper, and I need you to use one of my pairs of scissors. Okay? Go do that now. Alright, so hopefully you got your piece of paper, you got some scissors ready to go. I'm going to turn this guy off because it's a little bit easier to see that way. We're going to take this paper, we're going to fold it hamburger style, north to south side, but we're only going to fold each side into the middle. Okay, so we're going to go about halfway on each side, and you're going to do your best. It's not going to be perfect. I mean, mine will not, so it's okay if yours doesn't either. Alrighty, so far so good. right? We should have like a trifold looking thing, like a brochure with this side looking pretty meaty in the middle. And what we're going to do is we're going to take our scissors and we're going to cut in the middle towards each edge. So if you did this correctly, you should end up with this guy with 4 distinct flaps on it, okay? And now we're good to go. We can actually make our stab foldable. I don't need these anymore. Oh shoot, I probably should have thrown those. But we're okay. There's nobody in my classroom. I'm in my room, dude. Nobody's in here, we're good. We're going to now label each of these. S, T, A, and B. And let's see if you can kind of see that. S, T, A, and B. Alrighty. Okay? For stab, it's an acronym. Okay? So we'll put our little dots there too. Now, we're going to look at S together to start off. And we're going to go through each of these parameters and get them all situated. Okay? Let's do that right now. Alrighty, so let's take a look at this guy. So if I press play on T, it doesn't look like a whole lot is happening. But let's just kind of pay attention to like this guy real quick. And if I zoom in a little bit more, makes it a little bit more apparent. This guy is just shifting left and right. That's all that's really going on. It's just a horizontal translation. But it's a little bit interesting because notice as my t values increase, I'm going to the right. So positive values go to the right. Negative values go to the left. Okay, now why is that interesting? Because if I have negative 5.6 and I put that into this guy right here, it's going to look like bx plus 5.6. So actually, intuitively, it's the opposite. If you see plus t, or a plus t value, you're actually going shifting to the left. If it's a minus t, it means your t value is positive, you're going to the right. So let's put that in our stab foldable. Zoom in on this guy just a little bit more. And let's see what I put for t. Alrighty, and you can barely see that, so let's turn that off. That might be a lot better, okay? So it's a vertical shift. Positive, go up, or I apologize, we're on T. Spoiler alert. It is a horizontal shift, so if it's a positive T, it's going to the right. And it's going to appear as bx minus t, like I pointed out. You're going to apply this guy only to your x values, okay? So I also included the base x and y charts for sine, cosine, and tangent. You might want to include those on your stab foldable if you want to keep those handy. But if you're comfortable with them, you don't need to. Let's look at our next guy. We're gonna make this guy. Hold on. We're gonna go ahead. We're gonna do S this time because I already revealed it, and you know what S does because I just kind of told you. But if you didn't catch it, it is a vertical shift up and down. So if it's negative, it's going down. If it's positive, it's going up. So let's see on our stab foldable. It's a vertical shift. And again, you're only applying this to your y values. One thing to keep in mind, though, is you might have multiple transformations going on at once. You need to remember Pemdas, or order of operations. So multiply before adding and subtracting. Okay? So if you have two things that are applying to your y values, then you want to do this second, right? This is your addition subtraction, right? Let's go to the next ones. Well, if those are shifts, what do you think the other ones are going to be doing, right? So let's start with A. A is a vertical stretch and compress. So if it's positive, really what it's doing is and really it doesn't really matter if it's positive or negative. What I'm really trying to get at is whatever your y value is originally, it's going to multiply it by a scale factor of whatever A is. So, for example, sine of 90 is 1. Okay, so the y value is 1. But if I put your A value at 2, then sine of 90, or 2 sine 90, becomes 2. It just multiplied that 1 by a scale factor of 2. Same thing if I change it to 3, it does that as well. Same thing with our negative 90, it just multiplies it by that scale factor, right? If it's negative, it just does a complete shift about the y-axis. Or a complete reflection, rather, about the y-axis. So that vertical stretch compress, right? You're going to apply to your y values by a scale factor of a. And negative a will reflect it about the y-axis. And finally, let's look at b and what's going on with that guy. So b, let me put everything back to normal. So we have our constant. Well, that's why it's not showing up. A is 0. Yeah, if that happens, you just get a flat line. Okay. So b is currently equal to 1. Let's play that guy. Whoa, it's like an accordion, right? So this is a horizontal stretch and or compress. But it's a little bit unique because it's not as obvious of what's going on, actually. Because it's not multiplying by a scale factor of b, actually. As I get bigger, it's actually compressing it and getting it smaller. Whereas if it's a smaller b value, here's better, smaller b value less than 1, it actually starts to stretch out. Yeah. Okay, so what's happening here, almost just destroyed my mic, I just hit it. Sorry, bud. Horizontal compress stretch, you're going to apply it to your x values by a scale factor of 1 over b. And this does have an effect on your period. In fact, your new period will be 2 pi over b. So that is something to note. And the other thing too, sorry, trying to make sure this guy's recording. The other thing to note too is that if t and b both exist, it's actually a horizontal shift of t divided by b. Now, we haven't ran into any problems like that so far, and I don't believe the book actually does problems like that, but on the off chance they throw something our way like that, we're a little bit prepared. Okay? We're a little bit prepared. So let's actually see how these problems work in a problem-solving context. Because we actually haven't been able to see that yet. I don't think this guy is recording. Oh, it is recording. I'm dumb. Turns out I was recording the whole time, so that's a good problem. All right, we're good to go with it. So looking at these two problems, we're going to just graph these transformations of these graphs and apply those transformations that we just saw. And we're going to do it in a really nice, easy way. I think it's a really nice way of doing it. Start off with your XY chart where of your base sine function. So start with those angles that we did, 0, 90, 180, 270, 360, right? And get those y values down, 0, 1, 0, negative 1, 0. And now we just need to recognize what the structure is of this guy and what the parameters are. So these are our transformations, and that is our A, and that is our T. So I'm basically just multiplying my y values by a scale factor of 3, and I'm going to be adding, because this is positive, it's a positive 180, okay? I'm going to be adding 180 to these values right here, and then I'm just going to plot those on a graph that I make. So this is what I get as my new one, say new, okay? Again, just adding 180 to these guys, so that's 180, 270, 360, 450, and can I do it? 180. Just adding 18, 630. Phew. All right, and then your y values are 0, 3, 0, negative 3, 0. Righty. So now we have our x and our y values. I'm really going to just consider the positive side of this guy because I only have positive angles to really consider. And I'm going all the way down to negative 3 and going all the way up to positive 3. So how I scale this guy out, I think I'm just going to count, honestly. It doesn't really matter. I'll count by 180s. 180 is fine. 180, 360, 540, and then this would be 720. All right. No, we did not get to 720, but that's fine. So 180 is 0. 270 is in between these guys, which is actually why I picked a scale factor of 1, or a scale of 180 degrees. So I'm actually up here now. 360 is back to 0. This guy's down at negative 3 because that's where 450 is wedged in between. And then this guy Yeah, did I add? Whew, yeah, I added that wrong. I'm ended up at 540. What's going on, dude? Yeah, that should be 540. I don't know what I did. Just added wrong. Yeah. Yep, just added wrong. 540. Dang it, Mr. Knight. Okay. So our graph looks something like this, meaning it's just a little bit more, and it's a little bit more stretched out in the y. Okay. Nothing too crazy. And actually, this really isn't even like compressed horizontally. It's just, it looks like that because we're counting by 180s. So that's a little misleading, honestly, because this guy doesn't compress or stretch, right? It only shifts. So this guy's just shifted. That's all it is. It shifted from here to here. Number 2, we're using tangent now. And we got 3 parameters going on. That guy, that guy, that guy. All right? So that would be my A, my B, and my S, right? So now let's make our XY chart, our base one for tangent. Remember, we had -90, -45, 0, 45, and 90. And then our values. Tangent's really nice because that's undefined. 0, -1, and 1. All right. So let's see what our new XY chart's going to be after we apply our transformations. So let's look at these guys. So A, B, and S. So A and S are dictating the Y values, and B is dictating the X values. Now, B is the horizontal stretch compression, and it's a scale factor of 1 over B, in this case, 1 over 2. So I'm really taking all these guys and multiplying by 1/2. So half of these guys. So -45, this is -22.5. I can do that, but I can't add 180, whatever. 0, 22.5, 45, right? Now for the transformations of these guys. Well, we have 2 of them. Now, again, order of operations. I need to multiply these guys by 2 first, and then I'm going to subtract 5, right? And undefined's really, really, really nice, let me tell you, okay? So undefined, undefined. Cool. Now let's look at these guys. Times 2, -2, and then you're subtracting 5, we're at -7. All right. Yeah. That should work. Yes. And then times 2 of this guy gives you 2, -7 is -3, and then 0 times 2 is going to be -5. Okay. So now our tangent function looks transformed, and we can go ahead, we can graph this guy. A little bit different than this, we do need to consider the negative side, and I'll count by 22.5. That seems to be the easiest way to do this right now. Just whatever I had before. Because I got my undefined asymptotes here. 0, ooh, I almost messed up again, all right? We are using different y values, so we need to count up. I'll count up by, we'll go by 2s. 2, 4, 6, 8. -2, -4, -6, -8. All right, so 0, -5, that lands us about right here. 22.5, that lands us about right here. And then lands us about right here for -22.5. So this guy looks like this. It's just the tan graph that's been kind of just shifted down. Let's take a look on Desmos, what that looks like real quick. Alrighty. We had our A value is 2, our T value is 0, our B value was also 2, and our S value is -5. Just to check one of the values, right, we got 22.5 comma -3, 22.5 comma -3 along this is, yeah, we pretty much nailed it. Nice job, guys. Alrighty. This is Mr. Knight signing out. We will look over more of these problems later on, hopefully on Thursday, but we'll see. Alrighty. I would like to leave recording. Thank you.